Hello everyone, welcome to our Gaussian process tutorial. Today we are talking in the context of card pole balancing. When we work on card pole balancing, it's important to predict the future movement of the pendulum and we move the card correspondingly so that the pendulum stays balanced. However, in practice, the pendulum can fall faster or slower than our prediction. In either case, this modeling error can lead to the failure mode of the controller. Here is one example. Here is another following example. In practice, there are many factors that are beyond our model, for example, friction. Hence, we have modeling error. While it's not realistic for us to learn a model for each of these unknown factors, it's possible for us to learn a model that represents the distribution of modeling errors that allow us to reason about control in the context of uncertainty. For the carpal balancing problem in this tutorial, we choose Gaussian process to model the dynamics of the carpal system. Here we illustrate some key properties of Gaussian process on the right figure. So the Gaussian process model, first of all, can model arbitrary smooth functions. In this example, we would like to learn a reference function as shown in the right solid curve. We observe some noisy data around the ground truth. We use these data to train the Gaussian process model, which predicts values in the dotted blue line. While it predicts values, also predicts confidence intervals associated with these values. So Gaussian process not only output values but also the confidence intervals. Moreover, the Gaussian process for the training part with more data, it predicts values with less uncertainty. For the carpal, we define the states as a combination of four variables: the position, linear velocity of the card, the angle, angular velocity of the pendulum. The dynamics we learn with the Gaussian process model is discrete dynamics. We run simulations repeatedly with different initial state of the carpal and we observe the state changes over time. So basically we collect data pairs of current state and next state which forms the training set. Given an initial state of the carpal from the simulator, here is the ground truth of the falling trajectory, and we would like to compare the predictions from the Gaussian process model to the ground truth trajectory. Here we are comparing a predicted trajectory from a learned Gaussian process model in blue to the ground truth in red. The shaded area around the prediction corresponds to the variations of modeling error. As we can see, as time increases, the prediction has more and more inaccuracy with larger and larger variations in both angle and angular velocity. We cut off the trajectory in two regions. In the shaded box, we have larger uncertainty in the prediction. For our controller, it's more reasonable to consider the trajectory before the shaded box for more reliability. Furthermore, with more and more training data, our learned model predicts more accurately for both angle and angular velocity. Also, we can see the variations of modeling error also reduces for longer horizon. The Gaussian process learns the joint distribution of the training data, which is Gaussian with zero mean in our case, and the learned covariance matrix. Given a test input to the model, we make predictions based on conditional probability, which is also Gaussian with mean and covariance shown in the formula. Intuitively, we can view the prediction as an interpolation from the training data with the learned covariance. Let's consider an example on the right side where we gave a test input to a learned Gaussian process model. Interpolation means we make predictions of the test input mainly based on the values and variances of the training data nearby. Therefore, if we only move these three training data upwards and retrain the model, the movement of the prediction is almost the same. We have trained a Gaussian process model. How does the trained model help us to improve the performance of the balancing controller? We use a standard PD controller for comparisons. On the left side, the controller feedback on the current states. On the right side, the controller feedback on the future states predictions from the GP model. On the left side, the cart keeps moving to the right in order to keep the pendulum balanced. The feedback error is computed based on the current states and goal states. On the right side, the feedback error is computed based on the predictive states in the longer-term horizon and goal states. The pendulum stabilized earlier and the cart stopped moving earlier as well. It's important to point out that reduced uncertainty interval doesn't necessarily mean reduced overfitting. Sometimes, with more data trained for the Gaussian process model, we might be overconfident about a wrong prediction. The type of distributions that Gaussian process model can learn is also limited. We'll be discussing more about learning non-Gaussian distributions for controlling tasks in our TA projects as well. If you are interested in studying more about learning non-Gaussian distributions, here is a good reference to look at. Moreover, if you would like to study combining uncertainties into model-based control, here is a very good textbook to start with.